Hey everybody, we're still on chapter 17 and we'll maybe be finishing chapter 17 today, in which case we'll jump into chapter 18. I think we'll at least finish chapter 17, if not enter chapter 18, which kind of continues the theme of ketones and aldehydes and their reactivity. So remember, just a quick review. One of the things we learned about was the addition of alcohols, right? Addition of alcohols to ketones and aldehydes. And we learned about intramolecular just a little bit, but then the big one I think is intermolecular, which kind of means, you know, alcohol molecules that react with a ketone or aldehyde molecule. Like separate molecules. That's what intermolecular means, right? Intramolecular meant kind of within the same molecule. Okay. So yeah, alcohols did this thing, and we showed the mechanism of this. I'm not going to step through it all again. But this is a good general theme of how aldehyde would react with a dialcohol, and the two oxygens would essentially replace the double bond oxygen here, and you get the acetal. This thing's called acetal, right? Acetal. Let's write that down. I think it's acetal. Acetal, right? So that thing's called an acetal, and it was a kind of a fun mechanism. Protonate the aldehyde. We like to say protonate and then resonate. So we protonated it, then we resonated it to the RSCC, alcohol attacked, and then you have a oxygen with 3 bonds to it. It's positively charged. Proton transfer from the incoming oxygen to the oxygen that's going to be kicked off, right? And then the oxygen that did the attack kicks in, kicks off, and now you make a new RSCC. Right? So it first forms a double bond, right? And then the double bond resonates, and then you have a new, well, this whole thing, this resonating species is an RSCC. And then the other oxygen attacks, and then you finally lose the proton, and then you're at the acetal. It's a kind of fun, longish mechanism. Okay? What else did we learn about? We also learned that it was reversible, so you could go sort of backwards, and this just kind of shows how it was reversible in that you can go one direction, go from the ketone plus the dialcohol, kick off water to make the acetal, or you could go the other way and go from the acetal with acid water and cooking and kick off the dialcohol. And the mechanisms are pretty similar to go backwards. I'm not going to go through this mechanism again. The hydrolysis mechanism, you can see it again in the previous lecture. In a nutshell, protonate the oxygen, and then I guess that makes the right side oxygen a good leaving group. Left oxygen kicks it open, and then you have your first RSCC. Water's able to attack, and then it just kind of keeps going. After the nucleophilic attack, that's when proton transfer occurs to make a good leaving group. And this time it's the leaving group on the right, because our ultimate goal is a ketone, right? Because there's a hydrolysis mechanism. Anyway, so we learned about that. Also, we also learned about the use of these as protecting groups. I'm not going to review all of that, but since you can put them on and take them off, you can imagine the use of these acetals as protecting groups. So like that's protected as an acetal, then we'd use some Grignard stuff, turn the OH into a Grignard, and then eventually attach the extra carbon and then deprotect to the last stage. That's all last lecture too. We also learned about thioacetals. Thioacetal is the same thing as a normal acetal, except it's sulfur. And the only other differences with thioacetals was that you'd use zinc kind of as a Lewis acid in the attachment mechanism, and mercury as a Lewis acid in the detachment mechanism. So we talked a little bit about the mechanisms of those two, and yeah, that's kind of where we ended up. Oh yeah, there's one other kind of cool thing about those thioacetals, the sulfur-based acetals, and that was that there's kind of two ways you can sort of take it off. One is mercury chloride, HgCl2, and water, and that just does a normal deprotection, and you can kind of get the ketone out, right? So like it's just like hydrolyzing an acetal, which is the oxygen version. This is a thioacetal. But the other cool thing about thioacetals is you could actually kind of wipe off the functional group completely and leave yourself with an alkane, and that's using H2 rainy nickel. Rainy nickel is just a type of nickel that, in this case, reduces it off, so it just wipes it off and you get a CH2 group. Alright, so we're done with acetals and thioacetals, which I think was number 8. Now we're on to number 9, which is continuing the theme of like nucleophilic stuff adding to ketones and aldehydes. And now we're going to talk about nucleophilic addition of kind of nitrogen type things. Instead of oxygen type things, let's talk about nitrogen type things. And one of those things is ammonia, and we'll say amines in general. So ammonia is NH3, amines means like RNH2 or R2NH, like, you know, amines, amine functional group. Alright, so overview first. Kind of like the two things you're going to see are these. So, and they all have a pretty similar mechanism. If you react a primary amine, so that means one R group, so it's a primary amine. This does an equilibration type mechanism, kind of like the acetal mechanism, and the result is C double bond N, single bond to R, and this has its own funny name. This is called an imine. We went from a primary amine to an imine, and what do you think the byproduct is? We lost O and two H's, so you might make a guess and say it's water, and it is water. Yeah. Alright. So we're actually losing water in this mechanism. It's a dehydration mechanism, meaning water is being lost. It's a dehydration. Now if you do the same thing but with a secondary amine, and that just means a nitrogen with two R groups, or it could be a ring, like a 5-member ring or a 6-member ring. The big thing is two carbon things on the nitrogen. It does the same kind of thing, where it first makes something that looks like an imine. Is there any charges somewhere? Any charges like on the nitrogen with 4 things on it? Well, yeah, it's positively charged now. And so we have this theme where if things are positively charged, not everything, but a lot of things, the name ends in IUM. And this was an imine. This is imine with IUM at the end, which is iminium. So the name of this thing is called an iminium. And it's not done. So now there's like an irreversible step where essentially base, which is probably more the amine, because amines are basic. Base rips off this proton and kicks the electrons to make a double bond, and then up onto the nitrogen to make a final product, which is a little different. So you lost the double bond N. Now you have a C double bond C. And this has a third name. So we had imines, iminiums, and this looks like an alkene bound to an amine, right? Alkene bound to an amine. Any guesses on the name? It's an enamine. Enamine, okay? Alright, so the water is also produced kind of through the first step, but actually the water, because the water is produced, it's oxygen, hydrogen, and then this other hydrogen. So there is a net dehydration also. Oxygen, hydrogen, hydrogen, and so water is produced. I'm not showing it. Here it's very clear that it's all coming from the oxygen and the two H's on the nitrogen. Alright? Okay, so what's the mechanism of imine formation? Let's do that one first. Mechanism of imine formation. Well, you'll be very happy to see it's simple. It's a very easy mechanism. Okay, let's make a ethylamine. Alright. Oh, one thing, yeah, I should mention is that this is done under catalytic acid conditions. They're all done without H plus cat. Let's write it up here. H plus cat. H plus cat. H plus cat. All right, so they're all acid catalyzed. Okay, so the product is this. What do you think the mechanism is? Think back. How did we start the mechanism of the acetal formation? Because this is very similar to the acetal formation. When you have acid catalyst present, you have a C double bond O. Start by protonating the C double bond O. Protonate, resonate. Now you got your resonance stabilized carbocation. What do these react with? Is it a nucleophile or electrophile? Well, this is an electrophile, and so it reacts with nucleophiles, and the nitrogen's a nucleophile. It's got a lone pair. I'm just going to draw this one, sneak in and attack. Alright. I'll kind of go down. Okay. So now what's connected to what? This is connected to that. Okay. And where's my new charge? What's bound to four? Well, the nitrogen's bound to four things. It was neutral, but it gave up its lone pair, so now it's positively charged. Okay, and what do we always do after nucleophilic attack? Just think back. There's always something we do. It's two letters. Make something a good leaving group. So we want to make the oxygen a good leaving group, so it eventually goes away, right? So we do that with two letters. What's the two-letter? I'm going to call it a non-mechanism because I'm not showing a mechanism for it. PT means proton transfer. The mechanism, of course, is that I'm taking a proton and then giving it back. But we're not showing that. We're just showing the result of that two-step process. So PT is an abbreviated mechanism, right? Proton transfer. Take off a proton, give a proton back. And so now we got OH2 plus nitrogen, ethyl. Alright. There's my ethyl group. 2 carbons, right? And now we got a good leaving group. So nitrogen kicks off the leaving group. Not quite done, but we're pretty close. Let's go upward now. What do we got now? Protonated amine with a charge on what? Where's my charge missing? Got a charge missing. Where is it? It's on the nitrogen. Final equilibrium arrow. I just abbreviate, you know, this is also a case where I don't show the mechanism. I just say minus H plus. Minus H plus. If you wanted to show a mechanism, you could just say B dot dot, take a proton and put it back onto nitrogen. But this is an okay abbreviated mechanism for the last deprotonation. Cool. So there we go. That's amine formation. Kind of like acetal formation in some ways. A little different, but start the same way, and then nucleophilic attack, proton transfer, PT, and then kick off the leaving group, and then lose a proton, whatever. It's comparable to the acetal formation. Let's do C, which is the amine formation. Sorry, enamine formation. Okay. Alrighty. Let's do, what should our secondary amine be? I'll make it a 5-member ring. Okay, that's a secondary amine because it's a nitrogen with 2 carbons on it. H plus cat. Alright. And then the final product is the secondary, sorry, the enamine, right? Enamine. Technically, you know, we are making water, and where is water coming from? It's from the oxygen, that hydrogen, and actually the neighboring hydrogen on the ketone. That forms H2O. That's where the H2O is coming from. Alright, so let's do the mechanism. I'm going to try to sneak it down, going to the left a little bit because I'm worried about space a bit. So what do I start with? Protonate the ketone. Okay. What 4-letter abbreviation do I write now? RSCC. Of course, we resonate up to oxygen. Protonate, resonate. Uh-oh. Get rid of that line. Okay, good. Protonate, resonate. Got a plus charge that the nitrogen can attack now. Which side am I going to attack? I'm going to, for stylistic purposes, I'm going to kind of go to the left because the right is where the plus charge is drawn. Alright. Okay, so we protonated the ketone. Nitrogen attacks the carbocation. Everything's in equilibrium. Alright, so what do I draw now? OH. Nitrogen with a proton on it. 5-member ring. And what's the charge on the nitrogen? If it gave up its lone pair, attacked, what's the charge on nitrogen? It's positive. Okay. What do we always do after nucleophilic attack? 2 letters. What's the 2-letter abbreviation for the thing we do after nucleophilic attack? 2 letters. PT. Proton transfer. essentially from nitrogen to oxygen. So now we redraw OH2 positive, nitrogen, 5-member ring. Cool. Ah, we got a leaving group now. What do we do once we have a leaving group? What do we do above with the amine? We had a leaving group. We kicked it off with the nitrogen lone pair. Kick off oxygen. So what are we going to do now? Do the same exact thing. Lone pair. And what's it going to do? Kick in, kick off. Let's make it a little more clear. There, long arrow there. Alright, kick in, kick off. And that makes a thing that kind of looks like an imine, except it has a funny charge. Where's the funny charge? It's on nitrogen. So for that reason, we don't call it an imine, we call it a iminium. Okay. And what's the last step of... And the last step is usually irreversible to make the enamine. The last step is irreversible. It's an acid-base reaction where this proton now gets ripped off by some base, and I'll just draw B dot dot. Of course, the B dot dot is probably the same amine that you started with. So when I say B dot dot, it's probably that, right? The amine. It's a base. What's it going to do to make the enamine? Base takes proton, forms the double bond C, C double bond C, kicks electrons onto the nitrogen, and we've made our enamine. So, cool. All right. So that's the imine formation and the enamine formation. They're kind of related. They look kind of similar, right? Okay. So this is pretty obvious, but I'll mention it, and it kind of is something that you might imply, since all those steps are reversible, right? All those steps are reversible. That so if each step is reversible, what does that tell you about the reaction? I mean, the reaction could be reversible as well. So if I have a ketone and I want to make the amine, we'll say, propyl amine or whatever, you know, it's kind of like, how do I do that? What are the reagents to do that? Well, it's the amine, right? The amine plus the ketone makes the amine, right? Amine, ketone. So the reagent you would use is like propyl amine and H plus cat. And what's the byproduct? The thing that falls off, oxygen and 2 hydrogens, is water, right? Okay, and if I want to go the other way, I want to take the amine and wipe it off and replace it with oxygen. What's the reagent I would use there? Maybe something with oxygen that is very abundant in the world. Water, acid catalyst. And what's the byproduct? The byproduct would be the thing that falls off, essentially, the amine with the NH2, right? And of course, it's that. That's the byproduct, right? But where's it getting its 2 protons from? If it falls off, it would be an amine, you know, propyl NH2. But where's it getting the 2 protons from? I don't know, maybe from water. So, right? So when this amine goes back to the ketone, the byproduct is propylamine. Okay, and the H's are coming from water, and the oxygen is what gets incorporated into the ketone. Okay, so it's the same mechanism both directions, essentially. And you should try this. Try this at home. I'm not going to do it for you. Let's take cyclohexanone. Maybe this would be a good quiz question. I don't know. We'll see. Water. H plus cat to make that, right? See if you can do this mechanism. I'm not going to do it. Mechanism. I'll just tell you what the first step is. What do you think the first step is? It's the exact opposite of putting it, you know, if we're going this way to put it on, it's the exact opposite of that. So what was the first step? Acid catalysis. We'll protonate the amine, right? And then keep going from there. Make your RSCC. Maybe have water attack the RSCC. Proton transfer. Make a good leaving group. Blah blah blah, and make your way to the end. All right. So that's a general rule when you have these kind of reversible reactions, that the mechanisms are usually the exact opposite. Alright, so still on number 9, which are these nitrogen derivatives, amines, enamines, blah blah blah. Now we're on to something called imine-like derivatives. Imine-like derivatives. So they're like amines, but they're not exactly amines. They all have fun names. So I'm not a big, I don't make a big deal about testing on names, but I will mention the names so you're aware of them. One is if we react in a ketone or aldehyde with this stuff, it's called hydroxylamine. 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 What do you think it makes? Any guesses? It's kind of like an amine. It's an amine-like derivative, so maybe it looks like that. Kind of like an amine, but what's on the nitrogen? What group? Hydroxy group. Okay, and then you form, of course, water. It's the same kind of thing, same exact mechanism. It's the same exact mechanism, same mech. That'd be a good quiz question too. See if you can do the mechanism. And what's the funny name of this? They all have funny names. Each of these things has a funny name. This is called an oxime. Oxime. Okay, it's the same mechanism. The ketone gets protonated. You can try to draw that mechanism if you like. Ketone gets protonated, RSCC, nitrogen attacks, proton transfer, blah blah. Okay, what if we have a ketone or aldehyde and we react it with H2NNHR? Okay, so what is this thing? Well, we also have H plus cat. They all have cat. There's catalytic, so don't forget the word cat. Not a real cat, but a chemical cat. They all have catalytic acid, and this thing you may have never seen before. It's kind of based on that, which is NH2. If we say, imagine NH2, NH2, it's called hydrazine. Hydrazine. Hydrazine, Hydra, H-Y-D-R-A-zine. This is a hydrazine with an R group, so you might say substituted hydrazine, but generally speaking, it's, some kind of nitrogen thing. All right, so what's the product? Make a guess. It's probably, that, so the terminal nitrogen attacks and you do your normal amine stuff. And then this is connected to NHR. Okay. It has a funny name also. What's the byproduct? You know, your byproduct's always water. The funny name of this, if this is a hydrazine, you'll probably totally guess what this is called. Hydrazone. I don't think you'd guess that unless you read the book. Hydrazines make hydrazones. Hydroxylamines make oxenes. Mechanism, exactly the same. Same mech. When I say same mech, I mean same mechanism as an amine formation, because these are kind of amine derivatives. Okay. Another one. Do you see these from time to time in organic chemistry? And you know, just be aware of them. I mean, they're all just amine derivatives. Okay, I'm going to omit the reagent, and we can figure out what the reagent is for this one. Okay, so ketone plus something makes nitrogen amine derivative. This is called a semicarbazone. You also make water. Semicarbazone. So what do you think the reagent is to make this? Any guesses? It's something minus the R and the two carbons, right? So it's that, right? That's the reagent with an NH2 on there. So it's NH2, NH, C-double-bond-O, NH2, and that is, let's try to draw it. Okay, so it's basically the whole top thing, H2N. Yeah, so we definitely have a pattern here. I think the name of that stuff, I forgot what it's called. Something, you could have to Google it, or Wikipedia page or something. Semicarbazones are made from semicarbazide or something like that. I don't know what the name is. Yeah. Okay, so and so all of these methods, these the oxime and the hydrazones and the semicarbazones these are actually there's a lot of historical interest in these. They're called derivatizing agents. Derivatizing agents. It's kind of a early method for characterizing ketones and aldehydes. What do we mean by characterizing? Characterizing kind of means like for analysis, we're like trying to figure out the chemical structure of it. What's cool about them is they're often solids, right? They're often crystalline solids. Often solids. And when you have solids, you have well-defined melting points. Okay, so back way before we had NMR, we could do melting points like for hundreds of years. Melting points was a very easy technology. So in the old days, if you had a weird ketone, you could kind of figure out the structure of the ketone by making its derivatives, maybe oxime or hydrazone or semicarbazone, and then you look it up in a table. You're like, oh, well, the melting point is 85 to 90 degrees of this, and 100 to 105 of this, and 75 to 80 of this, and then you could kind of figure out what the ketone was because it would be in a table somewhere. So does that make sense? It's kind of like an old way we used to use to figure out the chemical structure of ketones. Now we get NMR. NMR is amazing, so this is not as used as commonly. Okay, so now we're experts at all sorts of additions to ketones and aldehydes, like we know about acetals and amines and enamines and oxanes and hydrazones and semicarbazones. We're going to go a step further and kind of show a cool reaction you can do to that kind of uses amine type derivatives and hydrazones for deoxygenation. Deoxygenation of ketones and aldehydes. What do you think deoxygenation means? It's that same idea we saw like with the rainy nickel as a way to kind of wipe off a ketone or aldehyde. Okay, and this has a name. It's deoxygenation of ketones and aldehydes with the Wolff, two F's, Kirchner reaction. So the name of the reaction is the Wolff-Kirchner reaction. Wolff-Kirchner. Sometimes they abbreviate the W/K reaction. Wolff-Kirchner reaction. All right. Okay, so what's the basic idea and what's the mechanism? The basic idea is that if we take a ketone or aldehyde, what we're going to do is we're going to react it with hydrazine first. This is unsubstituted hydrazine. So NH2 is unsubstituted hydrazine. So it doesn't have an R group on it, like we just saw the R group one. The other thing is that we're not going to use acid, we're going to use base, KOH. Okay, so the mechanism is a little different when you use KOH or a base. Okay, so no acid and we use KOH. It's still similar. The mechanism is similar, and you first make a what? What's the thing? Hydrazine reacts with ketones and aldehydes to make. It's just normal hydrazine to make an amine derivative. Okay. And what's that called? Hydrazines make something, somethings. This is a hydrazone. Okay. Now this is unstable with no R groups and in the presence of base. So we just kind of assume there's still base around, and then it just wipes off the nitrogens. And what do you think the byproduct is? What's a stable molecule that you're breathing right now that consists of two nitrogens? N2, right? That's the byproduct. That's a very nice byproduct because it's non-toxic. It's a pretty nice, happy byproduct. And it makes sense that maybe two nitrogens would kind of end up as two nitrogens, right? So, all right. So we got to show two mechanisms. We got to show the first mechanism, which is actually, you kind of know it, except the only difference is we're using base. Then we got to show the second mechanism, which you definitely do not know, is kind of how this hydrazone goes to wipe off the functional group, the hydrazone, to make N2. All right. So I'm going to show mechanism part 1 and mechanism part 2. Okay, first let's do mechanism part 1. So we're going to show how hydrazine, H2N and H2, makes the hydrazone. The difference here is we have KOH. We're not using acid as it's like we don't have acid like to activate the ketone, right? Alright, so We are making water. There's water being produced also. Okay, so the first step is not like protonation of the ketone, and that must be a little weird to you because so far every time it's like, oh yeah, we protonate the ketone. Well, one thing about hydrazine is that it's extremely nucleophilic. It's extremely nucleophilic, so it just loves to attack stuff, and it will directly attack the ketone without any help. No activation isn't necessary. So it just attacks the ketone, and what does that give us? Okay, so when it attacks, what do you got now? What do you got? Just follow the electron pushing. What's the oxygen charge now? It is negative, right? All right. And the nitrogen has how many protons on it? And it's got NH2, and how many protons on it? It's got 2 protons, right? And what's the charge on nitrogen? It's a plus charge. Alright, that's cool. Okay, now we can totally proton transfer because we it makes sense to proton transfer because O minus kind of wants a proton. It's going to be kicked off later. So it's got to be made into a leaving group. Nitrogen has an extra proton, so it's really easy to PT right now. So let's PT. Okay, I'm just going to put a square around my product there so we know where we're going. We PT from nitrogen to oxygen. Okay. Alright, so next we gotta kick off the oxygen. And the way I draw this, the nitrogen basically swings down and kicks it off. However, OH is kind of a bad leaving group, so what I usually draw is that we have some extra water up here, like OH2, and that kind of assists this OH in being a leaving group. So I just draw a little like a hydrogen bonding interaction. ... So this oxygen is kind of talking to other water around, and that assists in the leaving group. The departure of OH is a leaving group. So it goes away, and that's kind of assisted by additional water around. Some people don't even draw that, and that's fine also. It's just I don't like telling you about OH being a leaving group, because usually OH is not a leaving group, but this is a nice way to kind of show it. Actually, I'm going to do it a little bit better. I'm going to say OHH. Let's draw it like that. Okay. So, and let's draw this second arrow like kind of something like this. You know, you're in a sea of water, and this oxygen can kind of talk to other water and be made a leaving group. So this net effect is that OH is a leaving group. And you're also making a pretty stable functional group. The Hydrazone is a stable functional group, so it wants to form. Okay, plus charge. Lastly, what do? You got that proton, and we also have tons of base around, right? So this is an acidic proton, we have tons of base. So what's going to happen to this acidic proton in a sea of base? Hydroxide just takes it off, okay? Okay, cool. So that was part one. That was actually pretty straightforward, right? The only weirdness is that we don't have acid around, so hydrazine directly attacks. And once you do that, proton transfer, and from nitrogen to oxygen, and then some kind of departure of the OH as a leaving group, and then loss of the NH with base, and then cool. That was part one, which was the formation of the hydrazone. Now let's do the weirder step, which is the hydrazone to the alkane, right? Because we're making an alkane byproduct. Okay, so mechanism part two. Mechanism part two is the hydrazone. Alright, and this is all irreversible. NaOH or KOH, it's just OH minus. KOH, whatever. Hydroxide makes the alkane, and then you make N2. Nitrogen gas, okay? So how does that work? How does that work? Okay, so this is a little different. It's not that bad though. It's a fun mechanism. You got KOH, which is OH minus, super base. I don't want to call it a super base because there are bases that are much more basic than KOH. But generally speaking, yeah, it's a pretty strong base, moderately strong base. So it's a base. What do bases do? They take protons. So we're going to take this proton and kick electrons onto the nitrogen. Take the proton, kick electrons on the nitrogen. And what I'm going to start, the first couple steps are reversible, and then we're going to have an irreversible step. So NH what's the charge on nitrogen now? Took a proton off. What's nitrogen bound to two things in two lone pairs? You do your formal charge calculation. It's negative. Okay, good. Alright, so we have a nitrogen that's negative. Okay, and the next step is resonance. This is not an RSCC though. This is not an RSCC, and it happens to be kind of an unstable molecule. So don't say RSCC, because there's also not a carbocation. If anything, it's a carbanion because you have a negative charge. But basically, nitrogen resonates there and onto the carbon. So it does resonate to the carbon. It's just not a plus charge. It's a negative charge. And what's the charge now? We push electrons from the nitrogen essentially to the carbon. It looks like a frowny face down there, kind of, and it is sort of frowny, right? It's unstable. Carbon with a negative charge on it is, generally speaking, very unhappy. So that is an unstable carbanion, all right? And as a carbanion, what are one of the ways that carbanions relieve their unhappiness? Sometimes they're nucleophiles, like a Grignard is this kind of thing, and it's a nucleophile. But we have a sea of, like, KOH has water around, so we have water around, right? Now we're getting into the irreversible steps, because when this sees water as a base, this is a strongly basic carbon, the base can grab the proton, and that's a one-way arrow. That's not going to, like, go back and forth. Okay, so what I'm going to do is just go from the lone pair to the water, and cool. So it rips off the proton, right? All right, cool. What does that make? Proton. We just grabbed a proton. All right, we're happy and cool again. Now we have more base, OH minus. We have a lot of base around, right? And we're going to do it again. So the base rips off this proton, generates N2, kicks off another arrow to make another carbanion. This is where the N2 gets formed, N2, right? nitrogen. You can see, and that forms the triple bond in nitrogen, right? Base takes proton. These arrows go there. These electrons go there. That makes it N triple bond N, and it kicks off to break off the bond. Let's draw that nice and clearly. Okay. And that breaks the bond onto the carbon. What does that give us? It makes N2, which is that N2, right? And it makes R. Now we have another carbon ion. Okay, and then of course water just gives up a proton to that carbon ion, just the same as we did a second ago. And then we're done. Okay, so it's essentially the net reaction is base takes proton. You make this resonance resonating carbon ion. It's not really that stable. That's why it's so eager to grab a proton from water, but it is in resonance, and that's why the carbon minus it grabs a proton. And then you do it again. This time nitrogen is displaced as N2. You get a free carbon ion, totally unhappy. One of the unhappiest species in the universe. Carbon with a negative charge, with nothing else to stabilize it, is very, very unhappy. So in the sea of water, it just immediately grabs a proton, and now it's a happy alkane. Okay, that's the Wolff-Kishner mechanism. That's the Wolff-Kishner mechanism. Make a hydrazone, ketone or aldehyde plus unsubstituted hydrazine makes a hydrazone, and then in base this is unstable and forms the alkane. Alright, let's just show a couple examples of the Wolff-Kishner reaction, WK reaction. Here we have two ketones. Let's wipe them off the molecule. How do we do it? So first you make the hydrazone with hydrazine, KOH water, and it just wipes it off. We're assuming excess here, and generally speaking you can assume excess. They'd both react. Yeah, both ketones are wiped off the molecule. Okay. Of course, what's another way to do this? You know another way. This chapter even. What's the other way you could effectively do the same thing? Well, remember you can make a thioacetal with zinc chloride and react it with something. What's it? The thioacetal is the little sulfur thing. It's like 5-member rings. Sulfur, carbon, carbon, sulfur, right? Sulfur, carbon. Look up thioacetal. Thioacetal. Make thioacetal. A couple sections ago. And then we had a magic way to wipe off thioacetals. It was H2 something, right? Not palladium, it was rainy nickel. So rainy nickel is a formulation of nickel that does this reaction. Okay? Cool. Alright, so that's a cool example of the Wolff-Kishner reaction. Okay, so this is a pretty easy topic, but we just got to mention it. Number 11 is addition of cyanide. So cyanide means Cn minus, essentially. CN minus cyanide. Two ketones and aldehydes, and these the thing you make with these reactions is called a cyanohydrin. Cyanohydrin. You don't have to memorize names of things, but just keep that in the back of your mind. Cyanohydrin, and we'll see cyanohydrins later in the course also. So, but this is actually a pretty easy one. If I have a ketone and I react it with like NaCN, sodium cyanide, right? HCl, usually done with a little bit of acid. This is kind of just like a Grignard. So that thing's like a Grignard. It attacks the ketone. And what do you think the product is? Kind of like the product of a Grignard, right? That's actually pretty easy. And the name of this, what do you think the name of this is? This is a cyanohydrin. So it's a pretty simple concept. And the mechanism is totally crazy. I'm just kidding, it's very easy. It's just like a Grignard. So the Grignard attacks. Like a Grignard would attack, sodium cyanide attacks. What do you get? O minus, C triple bond N. And in a Grignard, it's usually like you do the Grignard and then step 2 is water, right? Well, in this case, you just have HCl present. So where are we going to get our proton from? Where's this O minus going to get its proton from? Well, we have acid around, so it just... So I'm sure you're relieved to have an extremely simple mechanism, and there is the extremely simple mechanism of this chapter to make a cyanohydrin. It's just CN minus NaCN, KCN, HCl. Makes that. Now these are interesting in terms of subsequent reactions you can do that are maybe a little later in the course, but we will see it again. So that's why we want to introduce it here. There's two things you can do. One is reduce the... what's that functional group called again? The whole thing is called a cyanohydrin, but this functional group is called what? C triple bond N is called a... I think chapter 1. It's a nitrile, right? Nitrile. So the whole thing is called a cyanohydrin, but that specific thing is called a nitrile. So one of the things you can do to a nitrile is react it with lithium aluminum hydride, which is just a super duper reducing agent, and then like water or acid. And that, what's this mechanistically equivalent to? It's mechanistically equivalent to H dot dot minus, right? So it's like it's an H minus source. It's essentially H dot dot minus, and you can imagine H dot dot minus would attack the nitrile and basically destroy the triple bonds, and that's exactly what it does. We'll see this again in chapter I don't know, 24 or something, of the amine chapter, of like how this would attack and basically give you an amine, and the end result is C triple bond N gets converted to C single bond N, which is essentially just an amine. So mechanism later, mech later. But you can imagine it's actually a very simple mechanism. H minus attacks, and then it actually just attacks again. So it attacks once, it attacks twice, and then you give some protons, and you're done. And so that'll be a fun way to make amines is from a nitrile. Okay. Right. So that's a reductive thing you can do to a nitrile. The other thing is not a reductive thing, but a hydrolytic thing, and that's acid water, H3O plus. So another thing you can do to a cyanohydrin, or we'll just say nitrile in general, is treat it with acid and maybe a little bit of heat. And of course, this is 3 bonds to nitrogen. What do you think happens if you convert 3 bonds to nitrogen to 3 bonds to oxygen? And that's what happens here, is you just make a carboxylic acid, right? So this is another fun thing to do. Okay, so that's the product of that reaction. That's the product of that reaction. This is a fun mechanism. This is about, I always say it's like a 20-step mechanism, but it's really about maybe 8 or 9 steps. But it's actually quite a mechanism to go from a nitrile to a carboxylic acid. It's really fun. I think it's next chapter or 2 chapters away. Yeah, probably about 2 chapters away. But we'll see this mechanism. Okay, for now though, you should just know one of the things you can do, or 2 of the things you can do, is cyanohydrins, or reduce them, which is reducing conditions, or hydrolyze them, and that would make a carboxylic acid. Okay. Okay, slowly wrapping up the chapter. We got a little bit more to do. Number 12 is another nucleophilic addition to ketones and aldehydes. That's what our theme, nucleophilic addition to ketones and aldehydes. This is addition of phosphorus ilids. Phosphorus ilids. Phosphorus ilids, and this is something called the Vitige reaction. And what's an ilide? Y-L-I-D-E. We'll explain that in a second. And the name of the reaction, though, is Vitige. And the pronunciation, well, the mispronunciation would be Witig. The mispronunciation would be Witig. We actually pronounce it like pronounced Vitig with a V. So the Vitig reaction, like with a V. All right. So the basic idea is this. And I guess what I'll say right off the bat, this is a way to make alkenes. It makes alkenes. So it's actually a really cool way to make alkenes through a nucleophilic reaction, and it's unique. It's a unique way to make alkenes. All right. The basic idea is this. Got a ketone, right? That's our theme of this chapter, ketone or aldehyde. Ketone or aldehyde. The basic idea is that we're going to add something and essentially make an alkene. That's kind of cool. That's totally unique. You haven't seen anything like that. That we could just magically take something and it would attack in a way that would make the alkene. All right. This thing that we're going to add is called a phosphorus ilide. With a E. Ilide. Y-L-I-D-E. It's just a funny charged phosphorus thing. It's a phosphorus-based reagent. Okay, and the name of it is called ilide. So what is the funny phosphorus ilide thing? The funny phosphorus ilide thing is this. And the mechanism is actually kind of cool and really simple. R prime, which is the R prime that we see in the product. And then dot dot minus. And then P, pH3 positive. Okay, so this, you can imagine what the mechanism might entail, and it's just that attacks, right? There's a little more to it, but carbanion, dot dot negative, nucleophilic thing attacks, and then, yeah. And so it does have a resonance structure itself, so this has its own resonance, and that's like if this just kicks down towards the phosphorus, what would it look like? It would look like R prime P pH3. Okay, so the ilide, all that means is it's the definition of ilide is adjacent positive and negative charges. That's what ylide means. It's just a carbon with negative, carbon with or phosphorus with positive. It's resonance stabilized, but that's what we mean by ylide. You can see though how this plus this kind of makes that. We'll see the mechanism in a second. Sometimes you can even like draw this and then like this kind of on top, and then you can see the relationship of like, you know, ketone and the ylide up top, and then like how everything in the middle kind of goes away and it makes the alkene. We'll see that in a second too. Alright, so first question is, how do you make the ylide? Making ylide. It's actually pretty easy. How do you make the ylide? Okay, so what we do, if I'm making an ethyl ylide, so we'll make the ethyl ylide. The way you do it is you first do an SN2 reaction. Very simple SN2. Go back to chapter 7 or 6 or whatever it was. PPH3. It's a simple SN2 reaction with a good leaving group, substrate, and PPH3. And the lone pair of phosphorus attacks. It's just an SN2. Nothing crazy. PPH3. But what's our charge now on phosphorus? Because it had a neutral charge and gave up its electrons. So 0 minus 2 electrons would be a positive charge, right? 0, right? 2 electrons are lost. It's a positive charge. Okay. So then all you do is use a super base like butyl lithium, super duper base. It's one of the strongest bases in the world, and that just rips off this proton. So it takes the proton and makes a negative charge on the carbon. Aha, there it is. That makes the ylide, right? So now you got PPH3 positive, negative. And this is in resonance, of course, as all ylides are. PPH3. Okay. Okay, so that's how you make the ylide. Then the next question is, once you got the ylide, what's the mechanism for ketone or aldehyde plus the ylide to make the alkene? And that's incredibly easy as well. So the mechanism, actually we're going to wait on that mechanism. We're just going to show an example of the reaction. We'll show the mechanism in a second. Example of like making an alkene. So let's just take benzyl, whatever this is, phenethyl bromide, and PPH3 and butyl lithium. I'm going to skip the intermediate, but this attacks, and essentially you get the ylide, right? I'll just draw P H PPH3. It's got its 2 resonance forms. PPH3 positive, negative, right? Okay. Let's draw a random aldehyde. And essentially what you're going to see is that, like, the bottom part of the ylide is going to react with the sort of the top part of the aldehyde and just make an alkene. And it's pretty straightforward. The product is that. Okay. So how does this react with that to make that? That's the next question. That's pretty easy. So let's show the mechanism of the Vitic reaction. Generally speaking, the first step you can imagine is just nucleophilic attack of the minus with the aldehyde. So negative charge attacks the aldehyde, just like a Grignard or something, and then just a little bit more stuff. Okay, so we're still on the Vitige reaction. And so what's the mechanism? So the mechanism is this. We'll just draw an aldehyde, and I'm going to draw my little Vitic, R prime prime prime, P, pH3 positive. We show it in the kind of this resonance form, right? We have the negative charge. We'll draw the product first, so the product is just the alkene. Cool. All right. The byproduct is going to be phosphorus, double bond O, phenyl, phenyl, phenyl. Okay. This is a super, super happy byproduct of phosphorus. Phosphorus loves bonds to oxygen. So when this all happens and it forms this, it's really happy. You can kind of see the relationship of the starting material plus the reagent, right? It's kind of like that and this, and they form the alkene. Okay, so what's the mechanism? It's really easy. So, carbon with a negative charge. What do you think the carbon with a negative charge is going to do to this thing with a negative delta plus, right? What do you think? It's like a Grignard, kind of, right? Grignards do what to ketones and aldehydes? They attack them. So it just attacks, alright? I'm going to draw this O minus thing, right? I flip this over in the mechanism. It's just to maybe simplify this a little bit. R prime, R prime prime. And the phosphorus is up here with a positive charge. Okay? That's all it did, is it attacked. And you have O minus, and the carbon's attached, everything's cool. This, now, you might even make a guess what happens. I have a negatively charged thing, I have a positively charged thing. What could possibly happen? They just form a bond. So negatively charged thing attacks, makes a bond to the positively charged thing. Okay? And what's that make? R prime, R prime prime? Yeah, it just makes a little thing like that. pH3. Okay? It just makes a little four-member ring, okay? This has a name. I never understood the name, but the name of it is, let's put brackets around the intermediates. The name of this is called beta-ene, spelled, if I was pronouncing it, I call it betane, betane, but it's actually, the correct pronunciation is beta-ene, and I don't really know what the history of that is. But anyway, the last step is very easy. It actually just falls apart. As you can imagine, just a concerted degradation, arrow, arrow. How easy is that? It just, 2 electrons go one way, 2 electrons go the other way. That makes this stuff, which is a totally happy molecule, and then it makes the alkene as the main product. It's the main product byproduct. Okay. Okay, so we're kind of wrapping up the Vitige. Just another quick example. Ketone. What if I have like pH3? This is, I just mentioned this earlier, like a cool way you can envision the product. If you draw the Vitige reagent in the double bound form, so it's like double bond to pPH3, you can easily see what the product is, the alkene. It's just like those two things snap together. See that? And then the byproduct, of course, is PPH3. Whoops, yeah, that's right. PPH3. And so that's a nice way you can do it. One more thought. If I was making this alkene, how could I do it kind of going backwards? I could envision we're going to make it from, I don't know, maybe ketone and PH3P, right? So you can kind of go backwards and say, I want to make that alkene, and I would make it from a ketone and the PH3P Vitic thing. And then you could make this from a couple steps from the bromide, right? Okay, so anyway, we'll talk more about that later. All right.